Hello everyone, I hope you're having a great day. Today we're going to go over the LeetCode problem greatest sum divisible by 3, including whiteboarding approaches and solutions. Greatest sum divisible by 3 is a dynamic programming problem with a little number theory sprinkled on top. So hopefully you've attempted a solution to the problem. If not, don't worry. The description reads, given an array named nums of integers, we need to find the maximum possible sum of elements such that it is divisible by 3. In other words, we're looking for the largest sum divisible by 3 using the numbers in the given array. Although it's tempting to use nested for loops, a solution to this problem is possible using a single for loop. Hence, we can achieve a big O of n worst case asymptotic complexity, which is pretty good considering the problem has its check combinations of sums, which can easily amount to a large quantity as the size of the list increases. The solution isn't apparent at first glance since it involves the divisibility of 3. So we can think of numbers as the sum of primes. In this instance, 2 and 1. So, which is 0. And so on and so forth. The pattern continues. You'll notice there's a pattern involving the numbers at the end of each sum. Right here, right here. There's a 1, 2, and then 1, and the next one will have 2. We can also express multiples of 3 like this. So the straight number that I've written at the end of each sum is the remainder when that number is divided by 3. Depending on which two numbers you sum, the divisibility may change or stay the same, so we want to keep track of that. For instance, summing a number that has a straight 2 in its sum representation with a number that has a straight 1 in its sum representation will result in a number divisible by 3. Similarly, summing a number that has a straight 1 in its sum representation with another number that has a straight 1 in its representation will result in a number that has a straight 2. And this continues for each pair of numbers with different divisibilities. We don't necessarily care about the groups of terms that sum up to an individual number, but rather the straight number, or remainder, since it determines the divisibility of the result when summed with another number. This logic is what will drive the propagation of the resultant sum. In other words, the maximum number divisible by 3 through to the end of the table, depending on which direction the iteration is taking place. So, considering this test case, I'm going to go ahead and force it to run. Right here, it contains 5 integers. The array may have unique numbers or it may contain repetitions. Counting the total number of arrangements of this list can be accomplished using this expression. Five factorial divided by 1 factorial times 1 factorial times 1 factorial times 1 factorial times 1 factorial, right here, is essentially equal to 5 factorial. This is because there's 1 8, 1 1, 1 5, 1 6, and 1 3. If the test case looks something like this, then our arrangements would be 5 factorial, over 2 factorial times 3 factorial. It should be obvious that this yields a relatively large number. The problem constraints also specify that the list may be at a maximum of 40,000 elements, so attempting to check every combination will result in a time limit exceeded. The calculation of 40,000 factorial will take an inane amount of time in itself. So since we want the optimal sum of numbers that will result in an integer that is divisible by 3, the approach will involve defining the subproblems as sums of 2 consecutive numbers and retaining the maximum sum for each divisibility. In order to accomplish this, the table will be structured like this. Where the rows correspond to the ith number in the array, and the columns correspond to the divisibility of that result. It is important to note that for each iteration, the resultant number in the divisibility column will always be greater than or equal to the previous iteration. This is what determines the optimal path. Now that the approach is determined, I will go ahead and write the pseudocode, and then we will move on to implementation. So first, we want to go ahead and define our table. You will see later on why I add a 1 to the size of the array. The table will have dimensions n plus 1 by 3 to correspond with the numbers in the given array. So next, we want to initialize the table for iteration since it currently contains only 0 values. This also covers the case that the size of a given numbers array is less than 3. Notice how I use the modulus operator here. I want to make sure that the first number that is set on that first row is set to the proper column. If we get under a given array of either size 1 or size 2, this will go ahead and exit properly. Now we can begin the iteration. As stated earlier, the asymptotic complexity of a solution is big O of n, so nesting loops isn't necessary. Since the current iteration of the table will contain the maximum result for each divisibility, the relation depends on the previous value for each divisibility. Each iteration will calculate the sum of the current number with the previous result for each divisibility, so we will begin iterating at index 1. For each column or divisibility, the sum in the corresponding column are calculated. The logic will look like this. Oh, actually, we don't need that yet. And here's the column. Now that the sum and the corresponding column are calculated, we want to set the result to its corresponding column in the current iteration. So then we go ahead and we repeat this for the next two numbers. The only thing that changes here is the index of the previous row that we're accessing. Since this is a little repetitive, I'm just going to go ahead and leave a comment. At this point, the columns for the current iteration are set to the maximum, or optimal result. One of the caveats of summing each pair of numbers is that the divisibility may or may not change, and there are instances where two different results with the same divisibility may be calculated. This implies that one result may be replaced. So in order to retain what we've calculated, we copy the values over to the next row before the next iteration. So maybe you notice that I have written row. That's just our index. So I'm going to go ahead and leave it there so you can properly examine. So this loop will iterate n times over the size of the given array. So finally, we want to return the result. Since we iterated from the beginning to the end of the table, the result will be in the 0th column of the last row. So note that if for whatever reason we never received or we never calculated a value that was divisible by 3, then the 0th column will be 0 and the function will return 0. It's right there. This is our algorithm. Now that the approach is written down, we will implement this in code. So I'm going to start by defining my table. Next, I'm going to go ahead and initialize the vector. Since it is guaranteed that the given array will always have at least one digit, we can do this. So you may have noticed that I have something right here that's a little cryptic or arcane. Essentially what this is doing is that it's making sure that this evaluation is 1. So this first not operator flips this number to 0, and the second one flips it just to 1. So I could have easily, probably, just written or typed down dp of 1, but there's a few edge cases that kind of rely on this, so I leave it in there. Right, next is our loop. Here we go. So first we calculate our sum. Next, we determine if that row or column in our current iteration is going to be replaced with the result of the sum. Next, we do the same thing for the next two columns. So yeah, it is as simple as changing the index in which we are accessing our previous iteration. Now, I probably could have written a for loop and it would still give me constant time for each iteration. But I chose to keep it like this because it was giving me slightly better performance. So now we go ahead and we copy over the values to the next row. Okay, and finally, we make sure that we return the correct value. From the 0th column. Now notice that I'm using nums.size and not nums.size minus 1. This is because I've declared this to be one more row greater than the size of the given array. There's several reasons for this, or at least one really good one. We want to make sure that we retain this logic without having to perform additional comparisons. So I go ahead and I do this right here so I can copy over to the next one without the program segmentation faulting. Okay, so now we go ahead and run. There we go, the tests are accepted. I'm going to go ahead and submit. And there we go, 34.03%. So before we finish, can we do this better? And the answer is yes, the solution can be further optimized. We could reduce the size of the table to a single array like this. I can go ahead and just get rid of this business right here. Now, there is one problem with going ahead and doing this. Since it's possible that two results may have the same divisibility, we want to store the results elsewhere in order to avoid overcalculating and to allow us to compare them against each other. So we calculate and store the sums first. Since our table is one-dimensional, I can just go ahead and get rid of the row access, and we just do it by the column. Can go ahead and remove this. So in this case, copying over the value over to the next row is not necessary. So we can just go ahead and do away with this. Finally, since the table is no longer two-dimensional, we just return the column. And we end up with this, which is a lot more concise. I actually like this a lot better. So now, let's go ahead and test this program. Oh, what did I do wrong? Oh, forgot. We actually can start at the 0th index. I just forgot to flip that. Right there, accepted. So we can go ahead and run this. And there we go, 89%. I actually ended up getting 99 at some point, but still a lot better than 34%. So to conclude, the solution will still iterate through the given list of numbers and store the optimal result in the table based on the divisibility of the results. Nothing really has changed except for that we're not consuming as much memory as we were before. Technically, I could probably turn this into an array. I tried a vector before, but that kind of slowed the program down a little bit since it was doing it creating a new vector each iteration. I found this to be the best result since it's possible that the compiler is actually placing these at the beginning of the method or function. Anyway, I hope this helped you guys out. I hope you enjoyed the video. I guess I'll see you guys later.